We discuss in this video about Boolean algebras and partial orders. And I start with a definition of what a partial order is. I say that for a set B and a relation this relation is called a partial order if we have following conditions satisfied. So it's got to be reflexive. In other words, it's got to be B smaller than or equal to B for all elements B in the set B. It's got to be antisymmetric. Meaning that if A is smaller than or equal to B and B is smaller than or equal to A, then A equals B. Finally, it has to be transitive, meaning that if A smaller than B and B is smaller than or equal to C, then A is smaller than or equal to C. And we call this a partial order, and I want to explain the word partial. So what I mean by partial, so this means that there may be elements A and B that are not in this relation, such that A is not necessarily in this relation with B, and also B is not necessarily in this relation with A. And in such a case, we just say that A and B are incomparable, and we denote this by this sign that is usually used for parallel, but we really say that they are incomparable. Another notation I want to make is I'm going to say that element A of B is a so-called smallest element. If A is smaller than or equal to B for all B in B. And of course, this is general definition, so I'm calling A smallest. I'm not assuming that this is the only smallest element. In many cases, there might be only one smallest element, but in general, there could be several, so I'm just saying A smallest element. In the same way, I'm going to say A is a largest element. So A largest in the same spirit if B is smaller than or equal to A for all B in B. And we are also going to say that A in B is a minimal element if we have A smaller than or equal to B, or A is incomparable to B for all B. So in other words, all the other elements are either larger than A or are incomparable to A. And in the same spirit, we have that A in B is a maximal element if B is smaller than or equal to A, or B is incomparable to A for all B in B. So with these definitions, we can also, in fact, associate a graphical representation, and this is called a Hasse diagram. So Hasse diagram is nothing else but just a graphical representation of a partial order. So Hasse diagram is going to be something like this. This is just an example, but it might look like this, that it has the form of a graph. And maybe we have elements A, B, C, and D, and also an element A. And what I mean in this example is that I'm going to write such a Hasse diagram in the case we have A smaller than or equal to B. So I'm representing this by having A on a lower position than B in the Hasse diagram, and there is an edge between them. And in the same spirit, from this diagram, I understand that B is smaller than or equal to C because B is lower than C, and there is an edge between them. And also, I understand from the diagram that B is smaller than or equal to D. And finally, we also get the point that C is smaller than or equal to E. Now, obviously, there are a number of other relationships between these elements. For example, by transitivity, we also conclude that A is smaller than or equal to C, for example, simply because A is smaller than B and B is smaller than C. So by transitivity, also A is smaller than or equal to C. But we don't indicate this by an edge because we can deduce it by following this sequence of edges, A to B and then B to C. And obviously there are other relationships. For example, A is also smaller than or equal to E, and B is smaller than or equal to E, and also we have A smaller than or equal to A. So all of these relationships that are either true for all the elements, like this one, the reflexivity property, or these ones that we have by transitivity, we don't indicate them in a Hasse diagram. So now going to Boolean algebras. So if I have a Boolean algebra B, I can define a partial order in the following way. So this can be defined for any Boolean algebra. So if B if this was a Boolean algebra, we define relation smaller than or equal to 2 in the following say. I'm going to say that A is smaller than or equal to B if and only if simply A times B, where this times is the multiplication operation in this Boolean algebra, is equal to A. So if this property holds, then I'm going to say A is smaller than or equal to B. And we have a number of properties that we can establish right away just based on this definition and based on the previous results we had in general for Boolean algebras. And I formulate this result here. This is lemma 2.13 in your lecture notes. And it says I have this Boolean algebra. So this is a Boolean algebra. And I consider the partial order that I just defined above here. So there are a number of properties that hold in general, and this is this relation is a partial order. And we will prove this in a moment. Second property that always holds is that A is smaller than or equal to B if and only if A times B equals A, if and only if A plus B equals B, and if and only if B bar is smaller than or equal to A bar. We have another property, and that's that A times B is always smaller than or equal to A. Then we have property 4, A is always smaller than A plus B. Property 5, if X is smaller than or equal to A and X is smaller than or equal to B, then X is smaller than or equal to A times B. Property 6, if A is smaller than or equal to X and B is smaller than or equal to X, then A plus B is smaller than or equal to X. And finally, property 7 is that if A is smaller than B and C smaller than or equal to D, then we have that A plus C is smaller than or equal to B plus D, and A times C is smaller than or equal to B times D. And a number of these properties are left for you to solve as exercise in your demos, and these are properties 3, this will be in your next demo, property 4, and property 6. But the other ones I'm going to prove now for you. So I start with the first property. And so the first property says simply that this relation is a partial order. So to prove that this is a partial order, we have to establish reflexivity. In other words, we have to check that indeed A is smaller than or equal to A. But so this is equivalent by definition. So this is the definition of our relationship, that this is A times A equals A. And this is indeed true by a result that we have proved previously about Boolean algebras, and this is formulated in your lecture notes in Lemma 2.4. The other property we have to prove, just so that we show that this is a partial order, is that this relation is antisymmetric. So if we take two elements, A and B, such that A is smaller than or equal to B, and B is smaller than or equal to A. So from this, by definition, what we get is that A times B is equal to A. And from this one, by definition, we get that B times A is equal to A. And of course, we know that in a Boolean algebra, so I'm just writing this one, A equals A times B. But in a Boolean algebra, we have that this property is commutative, so this is equal to B times A. And of course, B times A, I'm sorry, this was a mistake. B times A is equal to B. That was the definition. And so we get that B times A equals B. So in other words, we get what we wanted, starting with the assumption that A is smaller than or equal to B and B is smaller than or equal to A. We get that A is equal to B, establishing that our property, our relation is indeed antisymmetric. And finally, what we need to prove to show that this is a partial order, we have to show the transitivity. So to do that, I'm taking three elements such that A is smaller than or equal to B, and B is smaller than or equal to C. And somehow we have got to show that A is smaller than or equal to C. And by definition, what we get from this is that A times B equals to A, and what we get from this, by definition, is that B times C is equal to B. And so, to establish this, what we would have to show is that A times C is equal to A. So I start calculating what A times C is. So A times C is equal to, and I'm just using this property here. So instead of A, I'm going to write A times B. So this is going to be A times B times C. And remember that in a Boolean algebra, the multiplication is associative. And I have that this is equal to A times B times C. And I'm actually using this property now here. And so this is going to be A times B. And now I'm using this property just one more time to show that this is equal to A. And so we have that A times C is equal to A, which in fact implies that A is smaller than or equal to C. So we have established our transitivity relation, meaning if we have three elements such that A is smaller than or equal to B and B is smaller than or equal to C, we established that A has to be smaller than or equal to C. So that proves the property 1. Indeed, this relationship we have defined is a partial order. I'm proving now the second property, and that was that A is smaller than or equal to B if and only if A times B equals A. And in fact, this if and only if doesn't have to be proved because this is the definition of our relationship, but the other ones, they need to be proved. So the property was saying also that this is if and only if A plus B equals B, and this is if and only if B bar is smaller than or equal to A bar. And to prove this, this part is already established by definition. So I can focus on proving this part first. And so let's assume that A is indeed smaller than or equal to B, which by definition implies that A times B equals A. And what this means, remember that we have proved somewhere in a previous result, which was stated as lemma 2.5 in your lecture notes. And in fact, I'm using from that lemma just the second property that was established in that result. So in that result, we had that x plus xy was equal to x for all x and y in a Boolean algebra. So I'm going to use this property in this proof. So I would like to establish now this property. So I start by saying a plus b is equal to, and instead of a, I'm going to write a times b. So I'm just using this property. I'm going to use it here. So I'm going to say a plus b equals to a times b plus b. And this is where this lemma 2.5 turns out to be useful. By lemma 2.5, this has got to be equal to b. And so this establishes the property that a plus b equals b. So that was one side of the implication. And the other side is if, on the contrary, I'm assuming that a plus b equals b, then I would like to establish this left-hand side. For example, I want to establish that a times b equals a. So then I will have the following sequence of calculations. A times b is equal to, and I'm using this property here. So instead of b, I'm going to write a plus b. So this is going to be a times a plus b. And then using the usual distributivity property in a Boolean algebra, I have that this is a times a plus a times b. And again, I'm using one of these properties that we have proved for Boolean algebras. This is in fact formulated in your lemma 2.4 in the lecture notes. And the point is that this part is equal to a. So I'm writing here, this is equal to a plus a times b. And again, I'm using the same lemma 2.5, the same property that I used before. So lemma 2.5 here to conclude that this is equal to a. And so that's exactly what I wanted to prove. Assuming that a plus b equals to b, I'm proving that a times b equals to a. So that takes care of this equivalence part of the property too. Then the next thing I do to prove the last equivalence in this property is, in fact, I'm going to use the De Morgan rules. So I'm saying using the De Morgan, and you might want to check this in your lecture notes just to refresh your memory what the De Morgan properties or the De Morgan rules are. So using the De Morgan rules, what we are getting is, so on one hand, we have that a is smaller than or equal to b if and only if, by definition, a times b equals to a, and this is where I'm applying De Morgan. And in fact, let me just make one additional step, and I'm going to show you De Morgan in just a moment. I'm going to apply the complement for this relationship. So I'm going to have a times b. The complement of this obviously has to be equal to a bar. And this is where now I'm highlighting the De Morgan rules. And the De Morgan rules were saying when you take complement of a product, this is going to be the sum of the complements. So this is a bar plus b bar equals a bar. And this is going to be if and only if b bar is smaller than or equal to a bar. So that concludes the proof of our second property. And I would like to now make the point about the fifth and the seventh property in this result. So the fifth property we had was that if you have an element x which is smaller than or equal to a, and x is also smaller than or equal to b, then x has to be smaller than or equal to a times b. By definition, what this means is that x times a is equal to x, and what this means is that x times b is equal to x. So to establish this, I'm going to just simply calculate who is x times a times b. And now, because the multiplication is associative in a Boolean algebra, we have that this is equal to x times a times b, and x times a is equal to x, so that's going to be x times b, and x times b is equal to x. So we get that x times a times b is equal to x, and this now, by definition, it implies that x is smaller than or equal to a times b. So that establishes property 5. And finally, the last thing I wanted to show about this result was property 7. The other ones you will prove yourselves in the demos. The property 7 was saying if a is smaller than b and c is smaller than d for some elements a, b, c, and d, then we have that a plus c is smaller than or equal to b plus d, which is your usual summations of such properties, and also the usual multiplication of these properties. You have that a times c is smaller than or equal to b times d. So now the way this goes is, remember what this means. This means that a times b equals a, and this means that c times d is equal to c. So I want to establish first this property, and to establish that I need to calculate this multiplication, a plus c times b plus d, and I'm hoping to show that this is going to be equal to a plus c, but the calculation goes like this. This is going to be equal to a times b plus a times d plus c times b plus c times d, and this is equal to a times b. According to this property, this is equal to a, so that's going to be a plus a times d remains unchanged, plus this one remains unchanged, and then just writing it as b times c, and c times d is equal to c. So I have plus c here. So I continue with my calculations. So that's going to be now equal to a times, so when I'm looking at these two terms, I have a times 1 plus d, plus I'm looking at these terms, this is going to be b plus 1 times c, and this is obviously by lemma 2.5, I will have that this is equal to a times 1, because this one by lemma 2.5, this is equal to 1, and also by lemma 2.5, this is equal to 1. So I have that this is a times 1 plus 1 times c, so this is in fact equal to a plus c, which is exactly what I needed to show in order to establish that indeed a plus c is smaller than or equal to b plus d. And in the same way now, if I'm focusing on this property, a times c has to be smaller than or equal to b times d. So what I need to show for that is that when I take the multiplication, this will have to be equal to a times c. So let's see how this goes. I open the parentheses by associativity and by commutativity. So I come down to having a times b times c times d, and just for the lack of clarity, I'm going to even point out the way I want to multiply this. And again, I'm using this property, a times b is equal to a, so that's going to be a times, and C times D, again, this is equal to C. So it's A times C, which is really implying that A times C is smaller than or equal to B times D, meaning that this property is now also established. So this concludes the proof of our lemma 213. And I have now a couple of comments about the implications of this result. So lemma 2.13, among other things, was saying the following. It was saying, on one hand, in its property 3, that A times B is smaller than or equal to A. And obviously by symmetry, we also have that A times B is smaller than or equal to B. So if we think about the Hasse diagram, we have that A times B is a lower bound for both A and B. So I'm just saying here is the A times B is a lower bound for both, and I would say is a common lower bound for A and B. And also your lemma 2.13 was saying in its fourth property that A is smaller than or equal to A plus B, and obviously by symmetry also that B is smaller than or equal to A plus B. So what this means in terms of the Hasse diagram is that A plus B is a common upper bound. So A plus B is a common upper bound for A and B. But the point that I really want to comment on is really the properties 5 and 6 and what exactly do they mean. So property 5 was essentially saying, look, if you take any element x such that x is smaller than or equal to A and x is smaller than or equal to B. So if you take any other element x such that, you know, x is smaller than or equal to A and x is smaller than or equal to B, then the property 5 was essentially saying then x has to be smaller than or equal to A times B. So any such x smaller than or equal to A, smaller than or equal to B, has to be smaller than or equal to A times B. So I have to have this edge in here. So what this means is that in a Boolean algebra, so A times B is really the greatest lower bound for A and B. So what I mean by greatest lower bound is that any other lower bound for A and B has to be smaller than or equal to A times B. So that's an interesting general property. And it goes also on the upper part of the diagram. The property 6 of your lemma was saying, look, if you have any x such that A is smaller than or equal to x and B was smaller than or equal to x, let me just use a different letter just so that on the diagram I don't use x twice. Let me just use y. So A is smaller than or equal to y, B is smaller than or equal to y. And your lemma was saying in the sixth property that really A plus B has to be smaller than or equal to y. So on the Hasse diagram, what this means is that for any element y, which is larger, or if you like, A is smaller than or equal to y, but also B is smaller than or equal to y. For any such element, we must have also that A plus B is smaller than or equal to y. So what this means as a similar consequence is that in a Boolean algebra, A plus B is the smallest upper bound for A and B. So again, what I mean by smallest upper bound is that any other upper bound for A and B has to be larger than A plus B. I have one example to give in this video, and that's the example 2.14 in your lecture notes. In this example, if I take a set S, X, consisting of 3 elements, and I'm considering the Boolean algebra given by its subsets. So the Boolean algebra is going to be the set of elements are all subsets of X, and our addition is in fact union, multiplication is the intersection, the negation is the complement operation, and then we have the empty set as the 0 element, and we have the full set as the 1 element. So I'm thinking about this Boolean algebra, and I'm checking what does it mean in this particular algebra that A is smaller than or equal to B. So remember, by definition, this was that A times B equals A, which in our case, because the multiplication is the intersection operation, so this is going to mean A intersected with B is equal to A. And obviously, what this means is that A is included in B. So what we have is that in the case of this Boolean algebra, the subsets of a given set, the partial order we have defined is in fact coinciding with the inclusion relationship. So because X is a finite set and P of X is also a finite set, I can even show you the Hasse diagram. So Hasse diagram in this case is going to look like this. We have the empty set here at the bottom. Then we have the singletons. We have set P, we have set Q, and we have set R. And all of these are in a relationship with phi. Phi is smaller than or equal to all of these sets. And we have the subsets of cardinality 2, so PQ, PR, and QR. And now these edges, they represent inclusion, so obviously P is included into PQ, as is Q included into PQ. P is also included in PR, and so is R. And Q is also included in this one, and R is included in QR. And then here at the top we have the full set PQR, or the set X. And again, realizing that our edges really discuss the inclusion relationship, we have these edges. All of these sets of 2 elements are obviously included in the full set. Just one more comment I want to make before we finish this lecture, and that is that it's really important to realize that in any Boolean algebra, B plus dot bar 0 and 1, the smallest element is 0, and the largest element is 1.